Hello, everyone. Welcome to the Parsons Technical Webinar Series and our first webinar of 2026. I'll be your host today, Jessica Bennett. Today we have with us Greg Knight and Lauren Turner presenting on firefighting foam transition, PFAS cleanout challenges and solutions. We can go to the next slide. We'll go through a few housekeeping items first. We'll be keeping all phone lines muted during the presentation to keep background noise down. If you have questions at any point during today's webinar, you can enter them into the Q&A section at any point or hold them until the end to ask either in the Q&A section at the end or live by raising your hand, and then we can unmute you to ask your question. This webinar has been approved for 1 professional development hour or PDH credit. If you'd like to receive a PDH certificate, a link to an attendance form is posted in the Q&A section. There are 3 multiple choice questions there you'll need to answer, so please take a look at those that are also posted in case you have any issues getting to that link. If you have any problems or questions, you can contact us at danielle.savin@parsons.com regarding the PDH certificates. And finally, this webinar is being recorded and will be posted on our YouTube channel in the next few days. So just a brief agenda, we'll introduce our guest speakers, followed by a core value moment before we get into the technical presentation, and then wrap up at the end with Q&A. So a little bit about our presenters today. Greg Knight is with the TRS Group, a Parsons company, and will be referred to as either TRS or the TRS Group throughout the rest of today's presentation. Greg is the perfluoride operations manager overseeing the implementation of the perfluoride process on all TRS Group AFFF cleanout projects. He's been working exclusively on AFFF and PFAS cleanout since 2021, and he's involved in the remediation industry for over 3 decades. Lauren Turner is an environmental engineer at Parsons, supporting site investigation and remediation projects. She has leveraged her research experience to support the internal research and development program at Parsons with a focus on remediation of contaminants, including 1,4-dioxane and PFAS. And with that, I will hand it off to Lauren, who will present a core value moment before we get into the presentation.
Thanks, Jess. To get started today, Parsons has 5 core values that shape our identity, which guide company culture and the solutions we provide. The core values there are seen on the slide, and it includes safety, quality, integrity, innovation, and sustainability. Next slide. The highlighted core value for today is sustainability, which is a key component of services provided by Parsons, and we strive to develop environmentally healthy and environmentally conscious solutions, both at implementation and into the future. An additive that TRS has selected for use in the cleanout of PFAS containing AFFF from firefighting systems is perfluoride, and it will be the topic, a key topic discussed in the webinar today. In itself, it is a plant-based and biodegradable product, and it functions at ambient pressure and moderate temperatures, so it does not require high energy inputs to apply. This product has repeatedly demonstrated effectiveness without the need for hazardous solvents or specialized equipment. And beyond the product itself, AFFF changeouts or cleanouts permit the use of existing infrastructure and firefighting vehicles, allowing reuse and limited downtime. This can avoid the disposal or decommissioning of existing systems that are impacted by PFAS and avoids the installation of new systems, which could be resource intensive, both in materials, potentially carbon footprint, and also the cost. Lastly, the product perfluoride has been successfully applied for fire suppression systems, but also wastewater, providing itself to be a robust and environmentally conscious product with diverse application. And I'll now hand off to Greg.
Thanks, Lauren. Thought I'd start off before we dive in too deep and just kind of do a quick primer on what is AFFF. A lot of people may not be aware of it. AFFF is basically aqueous film forming foam. Is a very effective firefighting tool. Basically, it comes in a concentrate, and once mixed with water and propelled towards a fire with water pressure, it becomes a foam, and it's a very dense, thick foam that acts like a blanket. It basically is applied for, primarily designed for flammable liquid fires. So it creates a blanket between the flammable liquid that may be the fuel and oxygen. So basically smothers a fire. Why it works so well? PFAS. PFAS was designed to be persistent, and the bonds are difficult to break. So that foam is very dense and interlaid. So it's hard to break out. But why is it bad? Again, PFAS. We know they're toxic chemicals and they don't break down in the environment. So where is AFFF used? It's used in two different approaches, basically mobile systems and fixed systems. We're going to touch on the mobile systems first. One of the most common users of AFFF is airports, and they have specially designed vehicles called air rescue firefighting vehicles, known as ARFs. They are kind of a mobile fire station. They have an onboard water tank and an onboard AFFF tank. They can go to an event, fire, and not have to worry about hooking up to a water source. They've got tanks ranging from 1,500 gallons to 4,500 gallons of water. So they're self-sufficient. The operator or the vehicle driver does not even have to get out of the vehicle to apply the AFFF to a fire. Everything can be done from the cab of the vehicle. So very specifically designed vehicle for airport fires and airplane disasters, those kind of things. You will also find it in municipal fire trucks. Those are kind of your neighborhood fire trucks. Smaller tanks on those have AFFF, the tank with like 25 gallons, maybe 30 gallons, 50 gallons, typically under 100 gallons. But they have to typically connect to a water source, a fire hydrant. More rural areas, they will use an open water source. They can draft water from a pond or a creek for a water source. And they don't come across too many situations where they have to use AFFF. Exceptions maybe being a firehouse near a chemical facility or something like that. They also have trailers that are mobile. Trailers come in kind of two configurations. One is basically a vessel to carry more AFFF to large fires as a support vehicle. And then you have trailers that may have an onboard pump or a gas-powered pump, and you can connect to a hydrant and propel foam towards the fire. And then boats. You'll find these in large harbors and ports to help with fires that could break out on the docks, or gasoline fire on top of the surface of the waters. And then there's fixed systems, kind of the same concept, but stationary. You can't move them around. You'll find these AFFF systems in warehouses that store flammable liquids, manufacturing facilities of flammable liquids, hangars for airplanes, helicopters, those kind of things, fuel storage yards. You'll also find it too in chemical manufacturers. AFFF not only acts as a barrier to the oxygen and the fuel below the foam layer, can also suppress vapors, and it can be used as a vapor suppressant in a facility that may make hazardous materials, and there's a release. We'll buy some time for employees to evacuate. In the event of a release, the foam can be dispersed and keep that vapor layer down. So we're talking about firefighting foam transitions. Why are we doing this? The main reason is AFFF is no longer manufactured in the US. What you've got is what you've got, and if you have to use it and now you can't replenish it. So there's been fluoride-free foams being developed called F3. They've been developed over the years. Up until 2024 in the US, there was not a military specification fluoride-free foam available. About May of 2024, FAA decided, the Department of Defense decided, okay, we got a mil-spec foam. Now is the time to make the change. Obviously, we want to make that change because of PFAS again. The impacts to the environment from PFAS being deployed via AFFF into fires, firefighters being exposed to PFAS from the foam, and the liability management that comes with all of the above. Circling back to the FAA, they sent out a CERT alert. It's kind of a memo that they send out to all the airports. They said, okay, here's the guidance. We need to switch over from AFFF to fluorine-free foam. There was no timeline. It's just, heads up that we got to do this now. There are more mil-spec fluorine-free foams available now. It's not limited to one anymore. There's multiple brands on the market. And so we'll talk a little bit more about that. So, okay, we're going to transition from AFFF to F3. Why do we have to do an AFFF cleanout? Well, the primary reason is F3 and AFFF cannot be mixed. You add a fluorine-free foam to a vehicle that has some AFFF still in it, that formulation will not work well to put out a fire. You're going to be straddling the middle somewhere what AFFF can do and what F3 can do. The other reason is we want to get rid of that PFAS. Without doing a proper AFFF cleanup on a vehicle, you're going to have that continued firefighter exposure. You're going to have the continued environmental impact every time you release that foam and continued liability to the owner. Another reason is to clean out these vehicles is, like we said, the F3 and AFFF should not be mixed. And having a mixture in there could affect apparatus performance. But you could see some gelling of the new foam, clogged proportioners. A lot of things can happen that are clearly the manufacturer said just don't mix them. So you're thinking, okay, well, I'll just buy a new truck. I'll just sell the old one, put it out to auction. Well, the reality is for these ARF vehicles, for the airports, typically start about $1.5 million. And price goes up there as you add up the different options. If you add additional turrets or undercarriage, telescoping boom, all these different features that the vehicle have, the price point goes up. So, okay, we're going to make the decision. We're going to clean out our trucks. What are the roadblocks to doing a successful cleanout? Clearly, PFAS removal is the first one. PFAS, as designed, is persistent. It's persistent when you remove the concentrate. It is still residual PFAS remaining inside that vehicle. Trying to remove all that PFAS is a key point of doing a successful cleanout. Foam generation. Like we said, AFFF concentrate, water generates a lot of foam. There's not really too many other ways to get rid of that foam, the AFFF concentrate. Just, with water, you're going to generate a lot of foam. So one of the things you got to pay attention to is how much foam am I going to generate? And do I have a way to capture that foam so I don't have an unintentional release? Circling back to the F3, the F3, we know that we can't mix it with AFFF. Another requirement for use of F3 is you can't mix your F3s. If you buy one brand of F3 and decide you want to switch brands 2 years down the road, you can't. You cannot mix the F3s. AFFF, you could get away with mixing brands. They were very similar formulations. F3 are very different from brand to brand. Each company has its own proprietary formulas, and they just don't blend. So the manufacturers have been really clear. Don't mix your F3s. Don't mix with AFFF. Keep it dry. So that's a key component too. If you clean out a truck and you add F3 too soon, you're going to have water in there, and you're not going to have an F3 that is, designed to function as designed or as purposed. And the last thing is they want to keep it dry. Keep it dry. Keep it out of harm's way from water. Another challenge is the residues in the system. As we talked, PFAS is persistent. So is AFFF concentrate. There are a lot of little nooks and crannies in firefighting systems, both fixed systems and mobile systems, where AFFF concentrate can reside between flushing activities or cleanouts or between uses. Firefighters typically will drain their trucks of their water from all the lines after a fire event and bring it back to the firehouse. There are portions of that truck where the AFFF can remain. And typically one of those spots is between the proportioner and the AFFF tank, or in the lines on onboard loading pumps. A lot of these firefighting vehicles have pumps built in specifically to pump from a tote of AFFF or a drum, pump it into the AFFF tank. That little volume in there gets trapped, and the next time it goes into use, you could potentially put AFFF back in a truck you just cleaned out, recontaminating the whole thing. Waste generation and management. Again, we're dealing with PFAS. So you've got to make sure you have spill containment and controls over your AFFF concentrate, rinse water, generated PPE, and again, talking about that foam formation. If you don't have the capacity to handle that foam formation, you may run out of space really fast. And it takes a big footprint. You can see this photo on the right-hand bottom corner. Those are totes lined up with AFFF concentrate and rinse water. And that's just from a couple vehicles, and you've got all these totes taking up valuable real estate. Health and safety. That's a big challenge. Workers who are going to be doing this, performing these cleanouts, you're working with PFAS, worker exposure. You want to minimize that exposure to PFAS and have safeguards in place, be it engineering, administrator, or PPE to prevent contact. Another challenge too is especially specifically to airports, or airport indexes. Every airport has to have a certain amount of emergency vehicles on standby, ready to go at a moment's notice. You take one of those vehicles out to do a clean out, that changes the capabilities of that fire station at the airport to respond. So what is the airport going to do? You can borrow a truck from another neighboring airport or municipality. You can rent trucks. So that's kind of the whole shell game of trying to do a clean out, is maintaining these vehicles and maintaining that index. You take one out for service. Let's say the fleet's large enough and you have a second vehicle and a spare. So everything's good. You're cleaning out the truck, no problems. The other truck goes out for a daily test and all of a sudden transmission fails. Now you're down to one truck. You're out of index. If you can't maintain your index, typically that leads to canceled flights, delayed flights, and you know what that happens. That sets a whole chain reaction through a large portion of the country, that all of a sudden people are very angry and money's not being made. So a lot of people get very unhappy very fast. And the last clean out challenge is putting this burden on staff to clean out a vehicle and not understanding the challenges with the PFAS, the mechanics of the vehicle or system they're cleaning. Having someone unfamiliar with what they're doing can prolong the process and could lead to some costly mistakes. So what are our options if we're going to clean out a vehicle or a fixed system? The most common options, or I guess thought to be the most cost effective, are water only treatments, single rinse. The DoD has put out a memo that single rinse is adequate. A lot of people disagree. The Australian Defense came out several years ago with a triple rinse procedure. Basically, it's just like it sounds. It's like a single rinse times 3. So you're flushing the entire vehicle 3 times, collecting all that rinsed water and sending it off for some sort of just offsite disposal or destruction. There are a lot of options now to do more than just water. There are plant-based additives, reagents, solvent-based, glycol-based, and other technologies emerging quite frequently. There's a lot of new players in the field that are claiming and saying that they can do these cleanouts effectively. Another option is a combination of some of the above. You could do a water rinse coupled with a destruction technology and keep recycling that water through the vehicle as you're destroying the PFAS as it goes through. You could use an additive, one of the ones above, and use a flocculation or absorption through the carbon or ion exchange to treat that PFAS water on site or consolidate that PFAS into a manageable amount. So there's a lot of options out there, buyer beware. So I'm going to talk about specifically the perfluoride technology. TRS Parsons is the exclusive North American licensee for AFFF impacted applications using perfluoride. Perfluoride is a liquid substance. It was invented and developed by Martin Cornelissen in Essen, Germany. Cornelissen, he started the company Cornelissen Water Technologies. TRS, through some of our thermal work, have done some partnering with Cornelissen on some thermal remediation sites in Europe, and we developed a partnership. And Martin introduced us to perfluoride, and one thing led to another, and here we are. But going back to what Martin was trying to do, he was trying to develop an alternative to using carbon for PFAS treatment. But one of his key goals was to do no further harm. He didn't want to have exchange one hazardous material for another to remove PFAS, but create a new hazard on the back end. So he came up with perfluoride, and it's basically the ingredients are plant and food grade products enhanced in the lab. Was able to create this fluid. It's basically an acid that gets added to water, and it ionically bonds with PFAS particles to create a larger particle that can be filtered out. And again, it's biodegradable, as Lauren mentioned earlier in the first slide. So it's a safe, sustainable product. So how does it work? How does it look like when it works? So here's a little short video. This is kind of a flask in the lab. There's a stirring mechanism in play. It's a 1 liter flask, just AFFF, 1 part per million of AFFF added to potable water. And you can see after it stops stirring, these light, puffy, white, puffy clouds, a flock has formed with the PFAS particles and perfluoride. That's in the lab. Doesn't look like that in the field. The picture on the right, you can see that filtered flock. That's a lot more accurate to what we see in the field. It looks kind of muddy, kind of a brownish color, but the particles are large enough that it can be filtered out of the water. So you can pull the PFAS out of the wastewater, consolidate it, and then you have a small amount of PFAS, filtered flock to send off for offsite disposal. And then as far as the treated rinse water, there's multiple options, and we'll get into how we do that at TRS. So is triple water rinse enough? One of the things, we talked about earlier was water rinse is the misconception is that, oh, it's the cheap alternative. Well, maybe not. We were able to do a demonstration for a West Coast airport. They wish to remain anonymous, so it's confidential. We were able to take one of their vehicles and do a triple rinse first on the same vehicle, and then we finished the vehicle using perfluoride. It was basically a Pierce firefighting truck, had a 75-gallon foam tank on it with 3% AFFF. We did that first rinse. We collected a sample, and then we continued on and did the triple rinse with it as well. And if you look at this graph, it's in nanograms per liter total PFAS. This was a method 537 modified, so it was a shorter list. It wasn't the full 40 compound list, shorter list, but this is total PFAS. So we were almost at 63,000 nanograms per liter of total PFAS after the first rinse. We did the 3 rinses. We sampled that last rinse. We were almost at 66,000 nanograms per liter of total PFAS. We actually saw an increase in the PFAS concentrations. And then we finished our perfluoride. We did 3 perfluoride flushes of the truck afterwards. We got the total concentrations down to 394 nanograms per liter. Based on this demonstration, it kind of opened our eyes a little bit that you're really with water after 3 flushes or 3 rinses, you're only just getting started, just starting to crack the surface on the PFAS removal. So it's definitely something that you take into consideration. Talking a little bit, going back, talking about F3, about the issues with F3 if not managed correctly. TRS was doing a clean out at an airport. We were doing some of their ARFs. They had additional vehicles that were not part of the ARF fleet, but were at the airport. They self-performed a AFFF removal on these vehicles, and they added the F3. This was not the mil-spec F3. This was just a non-mil-spec F3 commercially available. The F3 gelled. I had mentioned that earlier. We don't know if it was in contact with water or some residual AFFF, but the gel to the point where the F3 would not flow. So the trucks were compromised. They could not apply the F3 in an emergency. So they were basically a water-only service vehicle. So basically TRS came in, we sucked all that F3 out of there. It was difficult to get all this out, but we cleaned it with perfluoride afterward and added new F3, the mil-spec in there, and the trucks were returned to full service. So again, that F3, you got to be really careful that your tanks are dry and prepared properly for F3. So what does it look like when you apply perfluoride in the field? Here's kind of a process flow diagram that gives you an idea of the treatment train. Hopefully you can see my arrow. So we got a mixing tank in yellow, you got a sedimentation tank in blue, we got the firefighting vehicle, we got some filters and some polishing carbon vessels. First thing we do is remove the AFFF concentrate from the vehicle. That's pulled out of the vehicle, containerized. That's got to be sent off site. Perfluoride is not a destruction technology. It does not destroy AFFF concentrate. It does not treat or remove PFAS from that concentrate. So that has to be taken off site. Typically, we apply a first rinse to the vehicle. We capture that and we sample that. So we take a baseline sample. That's how we determine our starting concentrations. That first rinse water is also containerized and sent off site. It's very highly concentrated in PFAS, typically too high to treat on site in a short amount of time. It can be done, but it's not cost effective. So it's cheaper to send that off site for disposal or destruction. So now that we've done that, we're ready to start flushing it. we have our mixing tank where we heat potable water up to about 120, 140 degrees Fahrenheit. We add our perfluoride dosing, mix it up thoroughly, and then we use external pumps. We pump from the mixing tank into the truck, into the AFFF tank, through the piping network, the foam distribution network of the truck. They've got, it's coming in and out of the bumper turrets. They got a roof cannon coming out of there. A lot of the airport firefighting vehicles have an undercarriage sprinkler. Basically, if they're fighting a fire and a fire creeps up or a fuel comes up under the truck, they can apply foam under the truck. So that way the truck and the driver are protected from the fire. So we flush all of those components. Everything in the truck is flushed, the proportioner, test ports, everything, the pumps, the loading pumps for the AFFF. Wherever foam has been, we flush it. We flush that for a predetermined amount of time, typically anywhere around 2 hours, basically. Once that solution is spent, we transfer it to a sedimentation tank, and we add a little bit more perfluoride, mix it thoroughly, and then we allow those flocks to settle. Like in that video, you saw the puffy clouds. Well, this time it's more of little brown particles, and we let that settle out. While that is settling, we'll go and prepare another batch of perfluoride solution and continue flushing the truck. So we'll do a flush, perfluoride flush of a vehicle anywhere from 3 to 5 times. And we'll talk a little bit about how we determine 3 to 5 in a little bit. Going back to the sedimentation tank, once that flock is settled, we're able to pump that flock from the bottom of the tank through a filter, capture that flock in a filter. That's PFAS and perfluoride. And once we see that the flock has disappeared from the tank, we'll transfer that to a different filter, and we'll send that remaining rinse water will go to just standard filtration, and then we'll go through carbon, small amount of carbon just to polish it. Whatever remaining PFAS is in there, we capture it with carbon, and then we send that to a holding tank. Typically, depending on the size of the cleanout, it could be a 5,000 gallon tank or it could be a 20,000 gallon frac tank. Capture that rinsate. Once that tank is full or we're done with the clean out, whichever comes first, we'll sample the tank, get analytical data, and typically we talk to the sanitation district before we start a project, but make sure we have discharge and approval based on laboratory results. We'll send those laboratory results to the district. They can review them and give us final permission to discharge. And then, the filtered flock gets separated. We pull those bag filters out and we let them dry, and then they're consolidated into drums. So you could go through clean 10 trucks and still have less than a drum's worth of quote unquote PFAS with perfluoride. So what does it look like in real life? This is kind of a cartoon. This is what one of our mobile batch treatment systems look like. You're looking going left to right. You see the stainless steel tank. That's the mixing tank. It's got heaters built into it. You can kind of see them over the secondary containment peeking out. All our pumps are powered from the control panel. The mixers, everything's powered from this control panel. You got the sedimentation tanks. The mixing tank has 1,800 gallon capacity. The sedimentation tanks, each tank has 1,500 gallon capacity. You can see the mixers on top, working platforms. Each sedimentation tank has its own dedicated pump for pumping the sludge or the filtered flock. And kind of hard to see, but if you look to the far right, you can see the water, what we call the water treatment skid. Got filter housings, there's 3 of them there, and then 2 carbon vessels. Very small, they're only 200-pound carbon vessels, so we're not using a ton of carbon. We're not trying to treat a wastewater stream with 1,000-pound vessels, 10 of them in series. We just have 2 in series with just a blend of different carbons that we find more effective for PFAS. Everything's in secondary containment. As you can see, the entire system's in secondary containment. And then you see in the foreground, we have secondary containment for the vehicle. The vehicle will pull up alongside the system and all the transfer hoses going back and forth. Here's a quick video, this is a little bit older, but it kind of shows the gist of how the process looks. Here's the perfluoride concentrate. It's got to be mixed daily before use. And you can see that color change, homogenizing, all that. It does stratify when it settles out. So it's got to be thoroughly mixed. And then once it's thoroughly mixed, we'll take a dose of that and we'll take it over to the mixing tank. Here's a mixing tank. It's got about 350 gallons of water in there. And you see he's not adding a lot of perfluoride. It's just a small amount. It's about half a beaker. So it doesn't take a lot of perfluoride. You can see how thick and viscous it is. It's like honey in color and substance. You see a little bit of color change. And then once that's thoroughly mixed, it gets pumped through the truck, and you can see the fire hoses here is attaching. We're pumping the perfluoride through the truck. It's coming through the truck and coming out. And then we got the return lines, and you can see this basically kind of a foam generation. Let's pause it here real quick. Now, this foam generation this is kind of a atypical first flush. And you see this foam generation on the surface of the water. That's the AFFF creating foam. It's doing what it's supposed to do. But that's kind of our indicator of how we determine if we were going to do 3 flushes, 4 flushes, 5 flushes. That first flush is pretty heavy in foam. That second flush is still foam. As we get further along in the flushes, we see less foam generation, and that's corroborated. Our lab data has indicated the same thing. We see that foam formation disappear, and all of a sudden by the 4th or 5th flush, there's very little to almost no foam being formed. Kind of gives us an indicator that we're done. So that's how we figure this out in the field. Again, this is the mixing component. So then at this point too, the next shot will show us pumping the perfluoride solution into the AFFF tank. There's a recirculation pump. You see the 2 green guard hoses recirculating the water, causing that agitation, having that perfluoride bounce off. And there's the sedimentation tanks. And here's a shot of the sludge getting consolidated, that filtered flock. It's pretty wet. We've refined the process since then in using filters, and now we can just drip dry the filters, and it's a lot more efficient and a lot less wet. It goes off as a solid waste as opposed to a wet waste. Again, this is kind of that same clean out. You can see all the debris that comes out, foam, but we're also seeing a lot of what looks like dirt and rust. In more rural areas, firefighting vehicles will draft water out of ponds and streams. That comes with a plus and a minus. You've got a water source, but you also get sedimentation in your trucks. Kind of a hidden bonus of using perfluoride. We're kind of cleaning the truck as well through that process, but we see a lot of rust, debris, but a lot of foam. This is just kind of calling out each of the components. You got the mixer, the heated water, and the return lines coming from the truck back to the mixing tank, creating that recirculation loop. Multiple passes of perfluoride solution through the truck, constantly colliding the perfluoride, colliding with PFAS on all those wetted surfaces and pulling that PFAS off those walls of the tank and the piping. I want to talk a little bit about the disposal aspect of using, a cleanout, really using perfluoride and a couple other technologies. So I use for this is just kind of a random example. I kind of let's have 2 ARF vehicles. These are 6x6, basically 6 tire vehicles. They have 420 gallon AFFF tanks. So I'm going to kind of go this horizontally, row by row, using a cleanout approach of perfluoride. We would have approximately 840 gallons of AFFF for disposal. So we'll go with everyone's going to have that. So basically the same thing. We got 840 gallons of AFFF. We're going to send that offsite. As I mentioned before, we do that first rinse of that AFFF tank. We're going to sample. That's our baseline. We're going to set that aside. We're going to containerize it. So we're going to have 840 gallons of water for offsite disposal. Now, typical perfluoride application, we typically generate cleaning out a truck with 4 flushes, 5 flushes, about 3,500 gallons of rinsed water. Using the perfluoride process, we can consolidate that PFAS, remove it from that waste stream, polish it with carbon. We've got about 7,000 gallons of water that we can send to the sanitary sewer. So we do generate some solid waste in this process. There's PPE. If you working with a vendor and there's no PPE for disposal, we're not doing it right. Every clean out activity will have PPEs. You're going to have, you just got to protect your workers. So there's got to be PPE. With perfluoride, we're going to have PPE. We're going to have some carbon. We'll have that filtered flock dried, consolidated, some tubing and some filters. Those are going to be your solid disposals items. So looking at perfluoride, we use perfluoride as our baseline for disposal. The rinse rate to the sanitary sewer, it's typically pennies per gallon for disposal, sometimes less. It's usually by the cubic foot. So you may be paying less than a penny per gallon for disposal. So it's a small cost. If you use a penny per gallon, you could say this is going to be, $70 here for disposal. Now, if we did triple water rinse with land, and this disposal we're talking about here is landfill. We're not talking about destruction, some of those other technologies. This is just landfilling. So if we do a triple water rinse, again, we're going to have 840 gallons of AFFF concentrate. That's standard. We expect that. Now you've done a triple water rinse on the truck, assuming there's going to be at least a minimum of 2,520 gallons. That's based on 420 gallon AFFF tank per vehicle, flush 3 times, times 2. You come up with 2,520 gallons. You should have more than that, but that's the minimum. You just clean the AFFF tank. As I mentioned before, there are areas where there's AFFF concentrate can be stuck in the system. So flushing the entire thing, you're going to have more than that. So that's got to go off-site for disposal. And those costs can be pretty, depending how far you go. There's a lot of other hidden fees with disposal. You've got transportation, analytical manifest profiles, energy fees, fuel surcharges, the list goes on. But we're talking just about landfill, you've got quite a bit of water there, and you've got to contain it or bulk load that out. So you've got to have some sort of containment. That's another cost. No on-site rinsate treatment, so that's not applicable here. Again, solid waste, you've got a minimum PPE, you've got some tubing you've got to get rid of. So you've got some solid waste and liquid waste. So looking at this scenario where all a triple water rinse going all to the landfill, it's about 40% more cost than using perfluoride. So, okay, let's look at another scenario. Triple water rinse with on-site carbon treatment. So I'm going to do a triple rinse, and then I'm going to store all that water, and then I'm going to treat it and send it through carbon and treat it on site and hopefully send it to sanitary sewer. So again, 840 gallons of concentrate. We're not sending any rinse water off site in this scenario, so no cost there. But now we're looking at a minimum of 2,520 gallons of water that you need to store somewhere before you run it through carbon. Solid waste, again, you're going to have PPE, you're going to have carbon, you're going to have tubing. I would recommend filters. It's not mandatory. But if you follow your carbon out because you don't have any particulate filters, you saw those tanks earlier with the mud and debris and the rust. You don't put that, it's going to follow your carbon, and all of a sudden carbon efficiency is going to drop, and all of a sudden your water's not coming out clean on the other end. What are you going to do? You're going to have to do it again. That's going to add cost. So you're looking at a cost, 40 to 60% higher, because you've also got to rent equipment, pumps, GAC vessels, carbon vessels, filter vessels, all that stuff, buying filters, all that stuff is not kind of part of that disposal cost, but it is a hidden cost. So disposal is part of the process here. You're not going to be able to just get rid of everything without cost. Wanted to kind of touch on that, show some scenarios. Perfluoride the goal is to minimize the amount of waste going off site. Looking back over the 4 years we've been doing perfluoride cleanouts. This is just US alone, not counting stuff that Cornelissen has done in Europe. We've done over 100 mobile and fixed system cleanouts. We've worked at 14 FAA Part 139 airports. Now that there are more options for F3, demand is increasing. People are calling, we're ready to do the cleanouts. They've observed the market and seen what's going on. A lot of our formal RFPs, a lot of direct contacts. We're expanding our equipment fleet to try to meet that demand. And we've got an experienced project team. I've been involved with all the perfluoride treatments from the beginning with TRS and now Parsons. And we've got an experienced group of field staff that are implementing the perfluoride technology. So how well does it work? I guess that's the next question. We're going to do a couple project look-ats or look-backs. We'll start with this one. This was a project we did. We completed it late 2024. LAX Airport, Van Nuys Airports. They're both airports operated by Los Angeles World Airports. So the Van Nuys vehicles were brought to LAX, so we just set up our equipment at LAX and did all the cleanouts there. We did 13 ARFs there. Rosenbauers, Oshkosh's, E1s. Those are 3 of the big manufacturers for ARF vehicles. And we also did one stationary tank. There was a 2,000-gallon poly tank outside the firehouse out there. The goals of the project, the on-site rinsate discharge. Treat that rinsate on-site and be able to discharge the sanitary sewer. And again, minimize the amount of waste that had to go off-site. Here's a graph. It's a little busy. This graph is in micrograms per liter, not nanograms. This one's in micrograms. You can see in the rainbow colored bars, that's the baseline concentrations. Again, total PFAS. These were EPA method 1633, so it's the 40 compound analyte list. Starting concentrations, and then in the very hard to see, but the low ones in green, those are the final concentrations. So you can see the pretty massive reductions. Our average final concentration in all these LAX vehicles were 1.4 micrograms per liter of total PFAS remaining in the vehicle. I have to say, kind of caveat, perfluoride, you will not remove 100%. I don't think any product will remove 100% of the PFAS. PFAS is persistent, but we typically see greater than 99% reductions from our baseline concentrations to our final concentrations. Looking at the rinsate side of things, again, we had 13 vehicles. We generated I think 4 frac tanks of rinse water through the process. This is a snapshot of just one of them. We took the trucks that we cleaned out, compiled the baseline concentrations, come with the starting concentrations here. This one's in nanograms per liter, so the numbers look larger. 2 million nanograms per liter. That was the pre-treatment total PFAS. Again, EPA 1633. After the rinsate treatment, that contents of the tank was down to 10.5. That was low enough. Again, nanograms per liter, so that's parts per trillion. 10.5 nanograms per liter of total PFAS in that rinse water. That met the criteria for discharge to sanitary sewer. We were able to send all that rinse water to the sanitary sewer from that project, 5.9 reductions. So perfluoride clearly working well. Another project here, this was another West Coast International Airport. This is not the one we did the triple rinse at. This is a different one. Again, client wanted to remain anonymous. This one was completed early 2025. We did 6 ARFs there and 1 stationary tank there. This one was 3,000 gallon fiberglass tank. Again, the goals, waste minimization, and again, being able to treat that rinsate on site and discharge to the sanitary sewer. Another quick shot of the cleanout results. In blue, we got our baseline concentrations. This is in micrograms per liter. The final in green, micrograms per liter, and then percent reduction also shown. Not as busy as the last graph, a little bit better, easier to read and see. Average reduction, we're talking 99.9% reduction of total PFAS in the vehicles. Again, with this project, we were able to send all the rinsate off-site. The AFFF concentrate went to disposal and landfill. And then PPE and that filter flock, all the solids went off as well. And quick snapshot, this is just looking back at the last half of 2025. These are the cleanouts we did. We are getting better at getting those final concentrations at that 1 ppb level. That's kind of an internal target we hit for our average here for those. These are different airports. 0.8 micrograms per liter. So we are getting better. We're always refining, looking back at our data, looking back at our processes, applying those lessons learned, and trying to get better every time, get better, get faster, get cheaper. So anyways, that's a quick snapshot looking back the last half of last year. And then fixed systems. I didn't talk too much about fixed systems. I want to jump into that real quick. Process is basically the same. There's a few variances that we do for fixed systems. Is a little bit more complicated. With a fire truck, it's all in one area. It's right in front of you. You can see it. Fixed systems, you've got a control room, or you've got a bladder tank or a AFFF storage tank, and then you've got all these valves and proportioners and everything out there. And then you've got an entire pipe network that could run all over the building or multiple buildings. So it's a little bit different approach, but basically the same. The dosing changes, the contact time changes, but basically the same process. And the next slide kind of shows a fixed system that we did a clean out. Similar, as you saw, as the airport reductions. This graph too, nanograms per liter. You can look on the left-hand side, you got the starting concentrations, tank 1 in blue, tank 2 in orange. Final concentrations, again, 80 nanograms per liter and 380 nanograms per liter, basically a 99.99 or better reduction in total PFAS. So as I stated before, we've been taking all this data that we've accumulated, doing all these cleanouts. We've taken more samples. to do additional studying and bench work. And I'm going to hand it over to Lauren to tell you what all this data we collected and what we're doing with it now.
Thank you, Greg. That's awesome. Yeah, I'm going to touch on some R&D here. So Parsons invests resources in research and development of diverse technologies for remediation and also characterization of contaminants. And the product for fluoride is a technology where R&D efforts are ongoing. Parsons has many talented researchers, scientists, engineers that investigate the development of technologies to meet client needs, and that includes data analysis and experimental work in the field, and then also the Syracuse, New York Treatability Lab. Relating to cleanouts, there are many parameters that can be recorded, and efforts to analyze this available data is ongoing, and it is used to optimize the perfluoride process. All TRS cleanout data is tracked, and this includes details relating to the cleanout rinse regime, much of what Greg discussed. So a number of rinses, fluoride rinses and water rinses. It includes the rinse volume of each rinse and then the total rinse rate, which is definitely important. If you are looking at PFAS concentrations, the amount of water used for the rinse is going to be relevant when you're getting your data in mass per volume concentrations. System characteristics such as tank size, the age of the system, and information about the manufacturer and model for both vehicles and also fixed systems. And then lastly, something that will also be tracked, and evaluated, are the compositions of the AFFF. AFFFs can be dominated by different PFAS and a variety of PFAS. And in tanks throughout the years, there may be mixes of different foams that have been put together or a replacement of a different foam with a different composition AFFF. And that's going to impact the PFAS that are on the interior surfaces of these fire suppression systems. And also the composition can influence potential analytical requirements if you're trying to evaluate data or concentration in your rinse water. So that is something to consider and something I will touch on again. The data set collected to date and data tracking that will continue into the future includes TRS cleanouts as well as Cornelison Systems cleanouts. And it's really going to support optimization to provide a cost-effective and successful solution to meet the current need to transition to fluorine-free foam. All right, next slide. Perfect. So I'm just going to do a little sidebar here to talk about characterization that will support some data I'll show on following slides. This kind of shows basically 3 analytical methods I focused on and what I've highlighted them and how they're kind of organized in this triangle schematic is to show kind of the breadth and proximity to total PFAS quantification. So at the top there, we have targeted analysis. So these are compound-specific analyses for select analyte lists that reference standards are available for. So this is analyzed via LC-MS-MS and would be a method like EPA method 1633. In the center there, we have TOP assay, which stands for Total Oxidizable Precursor Assay. And this is oxidative conversion of oxidizable precursors or fluorotelomers to target analytes that can then be quantified through target analysis, such as 1633. So it allows you to quantify compounds by the transformation to target compounds, and this is most often PFCAs. And then lastly, at the bottom there at the base, I've put total organic fluorine methods. So TOF methods, which can include absorbable or extractable organic fluorine, are non-compound specific, so they will not give you information about specific PFAS analytes, but they aim to measure total organic fluorine, which should give an indicator or a quantification of the total organic fluorine load to provide information on total PFAS. All right, we can head to the next slide. So we have some data here on this slide, and it's a plot showing info from a vehicle cleanout. On the kind of left separated plot, that is actually the AFFF product that was removed from the tank. And then on the right, we have data for the rinses, which includes the water rinse at the beginning and the final water. And then you can see those 3 perfluoride rinses in the center. The results indicate high performance of perfluoride with diverse analytical supporting these conclusions. So this includes the pre-top, so just the targeted analysis via 1633, and then post-top, so it would be after conversion of oxidizable precursors, which should give a better view of the PFAS impacts. So some key observations here. Based on the difference in PFAS concentration between targeted analysis and the post-top assay, we can see particularly in the AFFF and then the baseline water rinse and then into the perfluoride rinse that in this particular instance, the targeted analysis does not quantify PFAS impacts well because of the presence of precursors or fluorotelomers. So, this is reflected in a lot of PFAS research. It really demonstrates potential limitations to targeted analysis when you're looking at diverse mixtures of PFAS, and particularly AFFF, which are known to have fluorotelomers or precursors or diverse mixtures. With the application of the top assay, we really can see also the performance better. We see in that first baseline water rinse post-top that the concentrations are obviously lower compared to the AFFF that was pulled out of the truck, but definitely significantly reduced as we move from the water rinse through to the perfluoride rinses. And as we can see by the second and third rinse, that the concentration both pre and post-top, which gives confidence that PFAS is removed, was less than 4 ppt, and the final water rinse was non-detect for all the analytes in 1633, both pre and post-top. So with the application of the top assay, in addition to targeted analysis, we're able to really emphasize the results and demonstrate cleanout success. And in addition to the targeted analysis and top assay data included here, work has also been conducted to do organic fluorine analyses on samples of rinse water, which will further help with quantifying the total PFAS load in order to understand, what is in your truck and what's coming out with that baseline first water rinse, but also give you a better idea of how to assess performance if you know that you can really measure the total PFAS impacts. Thank you. Next slide, Greg. I want to touch briefly here on rebound. So this was a rebound study that was conducted for Nelson, and PFAS rebound after a cleanout was similar to the concept of back diffusion in the subsurface. And as many are familiar, due to PFAS's surface active properties and preferential partitioning to interfaces, PFAS can adhere very strongly to the surfaces. And there's also the potential for supramolecular PFAS structures or multi-layers of PFAS molecules on the internal surfaces of firefighting systems, not only on flat internal surfaces, but there's also a high degree of adhesion, where Greg mentioned there may be fittings or joints or texture in the pipes. The cleanout process not only needs to be able to remove, very accessible PFAS, but you really need the cleanout to remove PFAS found in layers or structures very strongly. When PFAS is not adequately removed, you'll get rebound of the contaminant into the replacement foam, which can occur, and the absence or presence, and I guess the magnitude of PFAS rebound can really be used to evaluate the cleanout conducted. If you have limited to no rebound, then you have a successful cleanout. However, these studies can be challenging because you have to sample the truck after a certain duration, and there's a high need for these firefighting vehicles to be operable. So it's challenging to take something offline to collect samples. And again, as we can see in this particular example on the plot, the leftmost marker on the plot is the foam concentration. And then we see the first rinse concentration, which is obviously reduced from what was removed from the truck. And then we have samples at 92, 203, and 702 days. And this includes a European analytical method with 26 analytes, and then also top assay with the 26 analytes. And the analytes, although not the same as 1633 with 40 analytes, it does cover mean PFAS, PFSAs, PFCAs, fluorotelomers, sulfonates, and then some ether-based PFAS as well. And so as we can see for those rebound samples, and in addition, there is a 1,000-day sample planned. With both targeted and top assay, we see very limited rebound, which suggests that perfluoride was successful for this system, and this is a vehicle system. that was cleaned out. And these samples were taken of the replacement foam. So 92 through to 702 days were PFAS analysis performed on the fluorine-free foam that was in the vehicle's tank. So ultimately, this data suggests perfluoride is removing adhered PFAS and not just superficial contamination. And as I mentioned, 1,000-day sample planned, and additional rebound studies are planned in order to use this data as a performance indicator. All right, we can head to the next slide. The previous slides have demonstrated some data for AFFF cleanouts, but there are additional parameters that are tracked in an internal project board. An assessment of this data and identifying correlations allows for process optimization, ultimately to provide an effective and efficient service that will help reduce PFAS liabilities and also limit PFAS distribution to the environment from fire suppression systems. And this includes TRS data as well as Cornelison data that will be tracked to provide a really robust data set representing both mobile and fixed systems that can be used for advancement of the perfluoride technology. So in the bullet points there, we can see some additional information that is logged. It includes system characteristics, vehicle type, make, model, age, which I mentioned, the AFFF formulation, and also the quantity in the tank that is removed. Rinsing regime, so that is the volume of rinses, how many rinses, total rinse rate. And lastly, those bottom two bullets on the bottom right of that list are really key factors, particularly with the mission to provide, a very high-performing service that is cost-effective. The duration and the price of these systems are obviously key pieces of information. This data will allow, us to better understand the cleanouts, identify where advancements can be applied, and really allows teams cleaning up these systems to anticipate challenges and potential nuances as cleanouts continue. For different systems in order to adapt and improve. Analysis of Cornelison and TRS cleanout experiences and also key results will be summarized in a journal article that is upcoming. So we're looking forward to sharing more information about the perfluoride technology and AFFF cleanouts in general. And hop to the next slide. Very briefly, just some demonstration of some cleanouts to date. So these are vehicle cleanouts, and we can see we have some data for truck specific parameters. The left is different tank size. So Greg mentioned there's a variety of different tank sizes that house AFFF, and the frequency or the number of cleanouts relating to tank size are highlighted there. And then on the right, we see the number per truck manufacturer. As we can see, many different manufacturers of fire suppression vehicles that there is experience with. Heading to the next slide. Greg did mention water treatment, so I will tag onto that. After the flocks are separated, the majority of PFAS is then sequestered, but there's a polishing step that is used carbon for the rinse water, and then after confirmation from analytical results, eventual sewer discharge can occur and the water is compliant. So the low PFAS concentrations can be effectively managed by the carbon. And although that method was discussed today, there are a variety of on-site methods that could be used for treatment of the PFAS impacted water associated with cleanouts. And this also includes destructive methods. So there are a variety of destructive methods that are available. And this could also include some of our Parsons developed technologies. And then highlighted on the slide there at the bottom, we see some photos. That includes the UV photochemical reactor. That a webinar was given on that technology last year, and if folks are interested, they can view that on the Parsons YouTube page. Destructive techniques could offer some advantages. You could have no waste or limited waste generation, and it would require any transport for disposal or further treatment, and this can lead to lower disposal costs, fewer logistical considerations, such as profiling your waste or scheduling waste pickup, and then you limit transportation overall, which something that could contribute to carbon footprint. And this is really kind of a environmentally friendly technology, as Greg developed. That was a key aspect in its development by Martin Cornelison. And also, if you can destroy the waste, you avoid any transfer of liability for concentrated PFAS impacted material. Next slide. And again, tying into that environmentally conscious thought, also our core value moment. just to revisit sustainability, that was a key consideration when TRS selected an agent for AFFF cleanouts. So, cleanouts and then for fluoride specifically support the reuse of infrastructure. This means less waste material, continual functionality of existing systems. This will limit downtime to operators and could also save costs, not having to replace certain systems, and they will be available for safety needs. The product itself, as mentioned, it is an oleic acid-based product, biodegradable, and this has advantages for both, field teams and persons on site, but also environmentally safer use, and also lowers risk in use, storage, and transportation when conducting cleanouts. So we can understand, the biggest risk of exposure during cleanouts is the PFAS, and as Greg highlighted, PPE is a very important consideration and is required. You have little to no requirement for specialized equipment when doing a perfluoride technology cleanout. This allows for ease and efficiency in implementation, as there are pumps, stirrers, and heaters involved. However, those are widely available, and it really does not take super high power requirements, and is not depleting non-renewable energy or scarce resources in order to implement and perform a cleanout. Lastly, very minimal waste. The flux has concentrated PFAS, and polished water is typically compliant, can be discharged to the sewer. And then to couple again with disruptive technologies, the incorporation of those can further limit waste to, really help with the environmental considerations and sustainability, but also cost as well. And next slide. Try to make this quick to be conscious of time, but to summarize, there is a significant and widespread need for cleanout or foam cleanouts for fire suppression systems. You really need to reduce and eliminate PFAS entering the environment, as well as limiting liability for both mobile and fixed systems in facilities such as like airport hangars and some other examples that Greg mentioned. Water rinsing alone has been demonstrated to be less effective for cleanouts than using the additive perfluoride, which can remove PFAS and also has been observed to limit or prevent the rebound of PFAS. The use and success of perfluoride, as Greg had described, is really related to the method in which it is applied. This includes heating and mixing of the perfluoride into a solution at optimal doses, and that perfluoride solution then recirculates through the firefighting system, and that is how ideal cleanout performance is achieved. And lastly, over 200 fixed and mobile fire suppression systems have been cleaned with perfluoride by TRS and Cornelsen. The data from these cleanouts is tracked and recorded, and we analyze this data to support optimization of the cleanout process with the goal to provide the most effective, efficient, and cost-competitive service in order to meet the current need for foam changeout in fire suppression systems. So that's all I have, and I think we can move on for questions if there is some time. Thank you.
Thank you, Greg and Lauren. That was a great presentation on the latest and the challenges and solutions, particularly for AFFF cleanouts. If there's anyone else that has questions who has not already posted in the Q&A, you can do so now. And if you have to either leave us before we get to your question, or if you think of anything else later, you can reach out to Greg or Lauren directly. Their contact information is here on this slide. And we'll also have the recording up on YouTube the next few days to a week. So let's see, we'll start with a question from James Yao. What's the most effective approach to dry the tank or on-site system after cleanout?
I'm gonna answer that one. Yeah, basically we just deploy an air mover that you would see for like removing harmful vapors from like a confined space. We just use one of those and just pressurize the tank, and that works pretty well.
The next question is, are your cleaning techs EVT certified? And I believe EVT stands for, are your cleaning technicians emergency vehicle technician certified?
No, they are not. We don't do anything to modify the vehicles. We work with the fire department personnel to get training on the vehicle before we start the work. So we do not do any like repairs or maintenance or removal of items. We'll coordinate with the fire department to do those kind of activities if needed. typically we don't get that intrusive.
Okay, next question is a little long, so I'll try and read slowly. Obviously, firefighter and equipment safety must be considered first when undertaking this type of operation. Before we introduce any foreign chemical agents into foam tanks for PFAS decontamination, what evidence exists that these products are compatible over the long term with foam system components such as elastomers, plastics, sensors, valves, electronics, and proportioners? And specifically, what OEM or independent third-party compatibility testing supports this approach that firefighter safety and system reliability are not compromised?
That's a lot. Yeah, that's a loaded question there. Well, perfluoride, again, is a plant food-based product. It's not harmful. We do recommend that the gaskets, on the hose ends or on caps be replaced because they will still remain, contain PFAS. Rubber is a good absorbent of that. We have no evidence that anything that we've used is damaging to the vehicles. It's a neutral pH. It's not acidic. It's not basic. Trying to think what other factors. We keep the heat to a minimum as we don't go over the heat rating of the materials on the firefighting vehicle. Yeah, I don't know if that answers the question or not.
We'll go to the next question. We replaced AFFF 2 years ago by simply pouring in the replacement foam to our foam tanks on our trucks. Do you know how long PFAS will persist and represent a concern to firefighters after changing to a PFAS-free foam?
Yeah, again, the manufacturers of the F3 recommend you do not mix with AFFF. So if any residual AFFF is remaining in that tank or in that system, you may have operational issues. You could see gelling. You could see just poorer performance. Yeah. And as far as rebound, you will see the PFAS will continue to rebound over time. The PFAS is persistent. It will come off the walls eventually and dilute back into the new foam.
Okay, it looks like we got one more question we'll take. For fixed systems, do you find the storage tank composition impacts the cleanout performance and rebound residuals?
Yes, 100%. Carbon steel is difficult, and the majority of these systems are made with carbon steel. So carbon steel does add an added layer. As I talked in the slide, it's a little bit different approach. There's some filtration that has to happen, for large particles. A lot of these pipes are old, rusty. So yeah, there's a lot of challenges with it, but the results are typical of what we see using perfluoride. Just it's a little bit more upfront preparation.
We said one more question come in. I understand this technology as a flocking agent to remove PFAS from solution, but is there an implication that it cleans off the walls like a solvent would?
We find that the perfluoride is able to remove that because of the agitation aspect, attrition, having pressure through the system and the perfluoride bouncing off the walls of the piping and the tank walls helps for that bond to occur where it can pull the PFAS off those wetted surfaces. And I think you can see the rebound studies kind of reiterate that.
All right, well, thank you to everybody who submitted a question. As I mentioned, if you have any other questions that we did not get to today or come up later, please feel free to reach out to Greg or Lauren directly. If we can go to the next slide.
Yep.
Our next webinar will be on February the 11th at the same time on PFAS and stormwater control measures, removal, distribution, and long-term fate, presented by Cesar Gomez Avila. Thank you to everybody who joined us for today's webinar, and we hope to see you again in February.